Hi everyone, this is Janine aka Janine The Tutor. As you all know, this is a very difficult time for each one of us, whether you're in middle school, high school, or university. Many students and families are deeply affected by the recent school closure. And as a part of OneClass, we are very fortunate that we are able to adapt quickly. And as a way for us to extend our helping hand, we are hosting free daily classes for math and chemistry. In addition, we are also giving away 100,000 hours of free private tutoring. And if you're interested, make sure to scroll down below and book your time slot. So for today's class, I will be going over grade 11 chemistry concepts. So we're starting from unit 1 until we get to the end of the unit. So without further ado, let's get started. Hopefully you guys can see my screen. If not, please make sure to just let me know. Okay, so a lot of students from grade 11, they come to me asking, okay, so how do I even master naming ionic compounds, molecular compounds, and pretty much all of the nomenclature in chemistry. So that's what we're starting off today. So even if this is not the first topic that they cover in Unit 1, I just wanted to address this right off the bat, just so to avoid any confusion. So we are covering ionic compounds and molecular compounds for today's class, and then acids and bases and hydrates will come on to the next live stream. So for ionic compounds, there's 3 different types. You have binary, which means it's only 2 elements that are chemically bonded to, and they're forming ionic bonds. And then you have multivalent. It's just 2 elements again, but the difference here is your metal. That means you have more than one charge. So it can carry multiple charges. That's why it's called multivalent. And then you have polyatomic, which means you have, say for example, multiple elements. So for example, you have non-metal CO3, right, which is carbonate. So it's not just composed of one element. So you have multiple elements, and as a result, you're forming a compound. Okay, so we start off with binary. So when you're naming binary compounds, a lot of students tend to use prefixes or even suffixes, which is fine for the non-metal component IDE, but you don't use prefixes for ionic compounds. And the reason for that is because you only use prefixes for molecular compounds. So within binary, so say for example, we're looking at sodium chloride. So we know that sodium, so let's go to our periodic table. So sodium is found in group 1. Okay, so sodium is found right here. It's found in group 1, and you have chlorine, which is found in group 7. So as a result, we know that sodium will carry a charge of +1 because your group 1 elements over here is likely to lose that electron to gain that full octet, meaning full valence of 8 electrons. And then for chlorine, because it's found in group 7, it's most likely going to gain 1 more electron to achieve that full octet. So that's why we know that sodium carries a charge of +1, while chlorine carries a charge of -1. So we first start off by writing the charges. And then we apply the crisscross method, or the crossover of your oxidation numbers or charges. So that means we have Na1, right? So that means your charge for chlorine becomes the subscript of sodium. That's why it's Na1. And then you have Cl1. That means the charge of sodium becomes the subscript of chlorine. And because for 1 we don't typically write it, that's why it's NaCl. So if we move on to magnesium oxide, that means we know that magnesium is found in group 2. So magnesium is right beside sodium. And then you have oxygen, so that means it's oxide because it's an ionic compound, and we change the spelling, which is IDE, right? Instead of saying oxygen, we say oxide. So oxygen is found in group 6. That means magnesium must carry a charge of +2 because it's found in group 2, and oxygen is found in group 6, therefore it must carry a charge of -2. So Mg plus 2, and you have O minus 2. When you cross over their oxidation numbers, you get Mg2, O2. And because we like to simplify things in chemistry, we are able to do that as well. So we just cancel out the 2, dividing all of the 2's with 2, right? That means you get MgO for magnesium oxide. So again, even though you only have one of these, right, one of the sodium and one of the magnesium, as well as chlorine and oxygen, you don't say mono, so we don't use prefixes at all. And then we only change the spelling by adding a suffix for your non-metal component. Okay, so moving on to multivalent. So again, ionic compounds, as you notice, they're all metals and a non-metal. Sorry, it's one metal plus another non-metal. That forms an ionic compound. So here, we're still applying the change in spelling, so we add IDE as our suffix. And then there's two ways to actually name multivalent ionic compounds. You have stock, which uses Roman numerals to indicate the charges, and you have classical, which is a change in the suffix. So depending on whether the charge is higher or lower, you would have to use a different suffix. So for the lower charge, you would have to use OUS, and for the higher charge, you would have to use IC as your suffix. So let's look at an example, which is FeCl2. So we know that iron, in this case, Fe, can have a charge of +2 or +3. So on your test or your final exam, I think you need to know what the charges are for your most common multivalent metals, because I don't think you're going to be provided with that. So just make sure you know that. So how do I know whether iron carries a charge of +2 or +3? So if you think about the crisscross method, right? Because the crisscross method applies for all ionic compounds, that means you know that iron in FeCl2 must carry a charge of +2, because when you crisscross, right, this subscript of chlorine belongs to iron, which is the charge of iron. Therefore, it's not really Fe +3, it should be Fe +2. And that's why when you name this, this would be iron 2, and this would be chloride. So iron 2 chloride. Okay, on the other hand, if we're using the classical way of naming, that means you're going to have ferrous, right? So ferrous chloride. So we take the suffix OUS because we know that iron carries the lower charge, which is +2, as opposed to +3. Okay, so moving on to polyatomic, we have, again, it's an ionic compound, therefore we have a metal and a non-metal. So the only difference between binary, multivalent, and polyatomic is for polyatomic ionic compounds, you don't change the spelling of your non-metal component. So in this case, if we look at CaCO3, we know that calcium is found in group 2, therefore it must carry a charge of +2. So let's go and look for calcium. Calcium is right here, so it's underneath magnesium. It's atomic number 20. Okay, and then we have carbonate, which is CO3. And again, these are your polyatomic ions, so you have to know what their charges are, because carbonate is a pretty common polyatomic ion. And you know that this is going to be -2 or 2-. And how do I know that? Well, the reason why it's -2 and +2, it's because if you think about simplifying 2, right? Because remember, the charge of calcium becomes the subscript of carbonate. That's why when you write this out, you would have Ca2, right? Again, this subscript was the charge of carbonate, and then you have CO3. So this is CO3 too, because you know that the charge of calcium is +2. So that carries over as the subscript of carbonate. And when you simplify this, you get CaCO3, which is calcium carbonate. And again, we don't use prefixes here, so it's only calcium carbonate. Okay, hopefully that makes sense, and we're now moving into molecular compounds. So molecular compounds, the difference between ionic and molecular is molecular compounds are consisting of two nonmetals. So for example, if we look at NCl3, so this is an example of a molecular compound. Why? Because we know that nitrogen is a nonmetal, and we also know that chlorine is a nonmetal. So here, this is the only time we use prefixes. So let's highlight that. There we go. Okay, so we use prefixes to indicate the number of atoms, right? So we don't use the crisscross or crossover of oxidation numbers here. Instead, we just look at the number of atoms. So if we're looking at NCl3, we know that this is a molecular compound. So when we name this, we say that this is nitrogen trichloride. And how do I know it's trichloride? Well, there's 3 atoms of chlorine. That's why it's tri. And an exception here is if you have the first atom, so in this case, it's nitrogen. If this first atom is a single atom, then that means you don't have to say mononitrogen. So you just keep it as nitrogen trichloride. And this does not strictly apply to nitrogen. It applies to all of your atoms. Okay, so here's the table. I think this is pretty straightforward. If you go back to middle school, like for polygons, when you're naming polygons, you would have to use tetra, penta, right? Like pentagon, so it's the same thing. Okay, so another thing that you need to keep in mind is if we're looking at, for example, P2O5, we say that this is diphosphorus, right? Because there's 2 atoms of phosphorus. Okay, so notice that this is 5 atoms of oxygen. So that means we need to use penta, right? So instead of saying pentaoxide, we would have to drop A because we have a vowel O, right? So instead of saying pentaoxide like this, it's a little bit awkward to have 2 vowels side by side, so we just drop A. So we would have to read this as pentoxide. Okay. That's 2 things to note for molecular compounds, and hopefully that makes sense. Okay, so here we have the IUPAC name. So IUPAC is just a way of naming for consistency because chemist likes to be consistent. As you know, chemistry is a universal language. That's why we like to keep names consistent. So for potassium phosphate, right? So we know that potassium is K+. And then we know that phosphate is PO4 3-, right? So again, this is something that you have to know, PO4 3-. For potassium, it's found in group 1. Potassium is right beside calcium. Atomic number 19. So again, because we know that this is an ionic compound, because potassium is a metal, right? And we have this polyatomic ion, phosphate. When you cross over their oxidation numbers or charges, you get K3PO4. So that's the molecular formula. And PO4 would have a subscript of 1 because the charge of potassium is +1. Moving on to beryllium sulfate. Beryllium is +2. Sulfate is SO4 2-. I apologize, I have to do all of the scrolling. I just realized that I should have included a periodic table that's above. It's a little bit cumbersome, but here, we need to deal with this. So, okay, so where were we? So we were at beryllium. So we were looking for beryllium. It's found in group 2. Therefore, this is atomic number 4, right? So it carries a charge of +2. Okay, there we go. So Be plus 2, and then you have SO4 2 minus, right? So when you cross over their oxidation numbers, you get BeSO4. And why is it BeSO4? Because the 2 cancels out, right? Be2, SO4, 2. It cancels out, that's why you have BeSO4. Okay, so looking at hydrogen chromate. So chromate is another polyatomic ion, which is Cr(O4) 2 minus. Okay, hopefully you guys can see the beryllium sulfate. So going back to chromate, so it's Cr(O4) 2 minus. So it's a polyatomic ion, and we know that hydrogen is carrying a charge of +1, right? Because it's found in group 1. So that means when you cross over their oxidation numbers, you get H2, and then you have Cr(O4). So that's hydrogen chromate. Now moving on to plumbic chlorate. Okay, so here's the thing. You have your suffix IC. That means it's a multivalent metal. So we know that plumbic is actually lead, right? So lead is Pb. So Pb, you can have +2 or +4 charge for lead, but because we know it's taking the suffix IC, that means it must carry a charge of +4, which is the higher charge. And then you have chlorate, which is ClO3 -1. So as a result, when you cross over their oxidation numbers, you have Pb, so this is 1, right? And then you have ClO3, and then you enclose that into a parenthesis, and you would have the subscript 4. So that's for plumbic chlorate. Moving on to titanium 4 phosphide. So as you can see, we have a Roman numeral 4 here. So titanium is +4. So phosphide, instead of saying phosphate, right? Typically we have phosphate. That means you're reducing 1 oxygen from phosphate. That's why you have PO3. And the charge would still be the same, 4-. So here's a trick to remember your phosphate, phosphite, and things that are ending in ATE for your polyatomic ions. If, for example, if you look at phosphate, so phosphate, we know that this is PO4. Sorry, I just realized phosphate should be 3-. Sorry, phosphide should be 3-. There we go. Okay, so phosphate is 3-, right? So the charge stays the same, so phosphide and phosphate. So you would have 3- as the charge, or -3. So the only difference here is if you have a suffix ATE, you would have 4 oxygen atoms if it's ATE. But if it's ITE, you would have to reduce 1 oxygen atom from phosphate. That's why it's PO3, right? So if you crisscross your oxidation numbers, you get Ti3 and close in a parenthesis PO3, then you would have 4. Because the charge of titanium is +4, that becomes the subscript of PO3. Okay, hopefully that makes sense. So now it's the other way around. We're supposed to turn the molecular formula into its IUPAC way of naming. So we have Li2SO4. So Li is lithium. And we know that you need to crisscross here because lithium is a metal, right? And how do we know it's a metal? So lithium is right beside beryllium, which is found in group 1. So lithium is +1, and we know that sulfate is SO4 2-, right? This is just going back to number 2, right? We dealt with sulfate right here, so SO4 2-. So that's why this subscript was the charge of SO4 2-. So it was formerly the charge of SO4 2-. So that means when you crisscross, that becomes the subscript of lithium. That's why we name this as lithium, because we know that it's an ionic compound. So this is lithium sulfate, and we don't use any prefixes. Okay, hopefully that was straightforward. So moving on to K2Cr2O7. So K2Cr2O7, this is actually dichromate. So this thing right here is dichromate. So yeah, you have to pay attention to chromate, which is CrO4 2- and dichromate, because they sound really the same and they're all with chromium, right? So dichromate, and this would carry a charge of -2 or 2-, and then potassium is K+, right? So when you cross over the oxidation numbers of the two, which is potassium and dichromate, the charge of Cr2O7 becomes the subscript of K+, right? That's why it's K2. So we call this potassium dichromate. So again, you don't say dipotassium. That's absolutely incorrect. So it's only potassium dichromate because it's an ionic compound. Okay, so moving on. So we still have 3 left. We have PbCl2 and we have Pb carrying a charge of +2. And how do I know? Well, lead is a multivalent metal, right? And chlorine carries a charge of -1. So this is an ionic compound. So again, we name this as lead-2 chloride. Or we can say this is plumbous because it takes the lower charge, which is +2 as opposed to +4. Plumbous chloride. Okay, so for CdNO2, this is cadmium, right? So first of all, where's cadmium? It's a transition metal. It's a multivalent metal. So cadmium is right here. So it's Cd+2, because we know it's a metal, therefore you need to apply the crisscross method here. And then you have NO2, which is just -1, right? Because as you can see, the subscript of cadmium is actually 1. That means the charge of NO2 would be 1. Okay, so we have cadmium, right? So NO2- is actually nitrite, right? So this is cadmium 2 nitrite. And again, remember what I said about having your polyatomic ion ending in ATE, and when you reduce one oxygen atom from that, you get ITE as your suffix. It's actually the same for nitrate as well, because nitrate is NO3-1, right? So when you reduce one oxygen atom, it becomes NO2-1. That's why it's called nitrite now. Okay, so moving to K2SO3. So K2, right? So SO3, 2-, and we have K+. So when you cross over their oxidation numbers, you get K2SO3. So that means this is potassium. So potassium sulfite. So this is the same thing which we talked about for nitrate and phosphate. We have sulfate. So sulfate is SO4 2-, right? So when you reduce one oxygen atom from sulfate, it becomes sulfite, which is SO3 2-. So the only difference here, as you can see, is the number of oxygen atoms to begin with. So for nitrate and for phosphate and for sulfate, it's 4 oxygen atoms to begin with, and then for nitrate you have NO3, right? Carbonate is also CO3, right? So just make sure you keep that in mind. And then when you reduce one oxygen atom, it becomes ITE as your suffix. Okay, so moving on to the theory. We're just going to be covering 3 scientists for now. Okay, so the whole atomic structure is it really began with Dalton. So Dalton was one of the scientists who really introduced the atomic theory. So what he said, right, was he was saying that all matter is composed of atoms. So there's only 5 main things that you have to remember based on his theory. He's saying that the matter is composed of atoms, and these atoms are indivisible, meaning you can't really destroy them further, right? So these atoms, if it's within an element, they're all identical. However, if the atoms are of different elements, so say for example, you're looking at oxygen, I'm not sure if you guys can see this. If you're looking at oxygen and if you're looking at hydrogen, right? So the atoms composing oxygen versus the atoms composing hydrogen, they're going to be different, right? Because they're different elements. So that's what he was saying for this point. Atoms of different elements are different. And then when you move on to the last point, he was saying whenever you have a chemical reaction, these atoms only rearrange themselves to form new products, but they're never really created nor destroyed, right? And why is that? Because matter is never created nor destroyed. Okay, hopefully that makes sense. And I just wanted to give a shout out to Nelson. So I got all of these images from Nelson, just so you're wondering where I found them. So it's from the textbook Chemistry 11. Okay, so moving on to Thomson. So this is J.J. Thomson. Fun fact, he's actually British, and that's why he, I guess the people just propose his model to be the plum pudding because it's actually an English dessert. So he actually did 2 experiments. Sorry, he actually did 1 experiment, and then based on that, he modeled that into a plum pudding. So really, he started off with the cathode ray tube. So essentially, this cathode ray tube, I'll draw this out here. Okay, so this cathode ray tube, there's actually 2 metal plates right here. And then he had this power source right here. And they're all connected to this power source. Sorry, this should be minus. So this has to be negatively charged, and this has to be positively charged. Let me just show that it's really connected. Okay, so he has this source right here, which is the power source, and then there's 2 metal plates. And then he noticed that this started creating or shining a beam of light, and it was going in this direction. So it was sort of slanting upwards, right? And why is that? Well, when he applied electricity, so when he had a plus charge here, that means this negatively charged metal plate is attracted towards this positively charged. That's why it doesn't go in a unidirection form, which is just a straight line. It actually goes towards the positively charged source right here. And when he attached a magnet, as you can see there's a magnet here, this also diverted the direction of the beam of light. So for example, if you attach a magnet right here, so just assume, okay. Sorry, for some reason I think this just creates its own shape. Okay, there's supposed to be a magnet here. So just imagine that the circle is a magnet. And then once he applied a magnetic force, this beam of light diverts its direction towards the bottom. So again, it's not a straight line. So as you can see, the way he proposed this experiment was he was saying that within this cathode ray tube, there must be something that's negatively charged, right? So we have particles within this cathode ray tube that's negatively charged, but at that time, he didn't really know whether they're electrons, but now we call them as electrons. So he was actually the first person who discovered the electrons. Okay, so that's how the cathode ray tube worked. And then he also proposed the plum pudding model. So essentially, if you think about like your chocolate chip cookies, so the chocolate bits are your electrons, and then he was saying that this chocolate chips or these right here, they're actually surrounded by positive charges. So we have electrons that are surrounded by positive charges, and hence that's why we have the plum pudding model. So that's how he kind of visualized it, which he found out about the electrons. Okay, so far, I think I've covered that. Okay, so the next person would be Rutherford. So he was the one who proposed about the nucleus, and how did he found out about the nucleus? Well, that's because of his gold foil experiment. So let me try to zoom this in, if you guys can see the picture. Great. Okay, so the whole point of this is you have your source here. So these are where the alpha particles are being shot, right? So this is your alpha particle source. And then you have a gold foil here, right? So this is your gold foil. So essentially what Rutherford was saying, if Thomson was right, that means he is expecting that the alpha particles, they're going to pass through the thin gold foil. That's when, if Thomson's proposal was right. However, what he found was these alpha particles coming from the source, they all did not just pass through the gold foil, because some of them deflected, right? So what's the reason behind that, right? So as you can see, we have this deflection of some of the alpha particles, but the majority of them went straight through the gold foil, right? So here we have this deflection. So he was saying that for the alpha particles that deflected, there is a positive charge mass or center in this thing right here, which are composed of protons, right? So they're positive charges that are centered in the atom's mass, and as a result, that causes your alpha particles to deflect back, right? Because positive charges, right? The alpha particles are positively charges, and then you have this nucleus in the middle, which is also positively charged, right? So that's what caused the alpha particles to deflect back. So that's what he proposed. And then for the alpha particles that pass through the thin gold foil, these are based on the fact that your atom is consisting of mostly empty space, right? Even though you have your electrons surrounding your nucleus. So that's what he proposed. And I've written that down right here. 2 findings: some alpha particles, they deflected, and then some of the alpha particles, they passed through. And the reason why that happened. So in fact, Thomson was actually incorrect, because some of the alpha particles deflected. That means your electrons are not equally distributed. And you do have a centered mass, which is your nucleus in the middle, consisting of protons. Okay, so moving on to Bohr. So Bohr was really responsible of proposing the planetary model, right? So as the word implies, it's the planets orbiting around the sun, for example. So as you can see, we have what we call energy levels, right? So where the electrons are specifically located. And each orbit has a specific quantity of energy, right? So he's saying that energy is quantized. And as you can see, even though we have various energy levels, so we have n is equal to 1 until 6 or even more. Actually, it should only be until n is equal to 7, because if you check your periodic table, we can only have n is equal to 7, right? Which is your period, right? We only have 7 periods in our periodic table, right? 1, 2, 3, 4, 5, 6, 7. So what he was saying, that these electrons, even though they're located in a specific orbit, they are able to absorb energy and they are able to emit energy based on whether they're jumping from a higher energy level towards a lower energy level or vice versa. So that's what he proposed. And also, the way he set up his experiment was he had this, again, this is a source, this is an electricity source, and then he had thermal energy, where he also had a prism which sort of directs which direction the light goes, and behind that you have a screen, right? So what he noticed, that hydrogen has discrete lines or light, which is very unique to its own. Does that make sense? Which is very unique to its own. Okay, there we go. Okay, so let's move on to elements and basically identifying how many protons we have, how many neutrons, and how many electrons. Okay, so this is just a quick refresher. So we have, first of all, we have what you call your element, which typically we denote it as X, and then we have your atomic mass and atomic number. Okay, so this Z right here, this is your atomic number, right? So atomic number just means it's the number of protons. And how do you know what the atomic number is? You just look at your periodic table, and it's basically this thing right here. So here you have 1, for helium you have 2, and then so on and so forth, right? Until you get to 118, right? That's your atomic number. It just gives you the number of protons. And then you have what you call your atomic mass, right? So atomic mass is A, and that's basically the weight, right, of your element. So in this case, we see that your atomic mass is actually based on the sum of the number of protons and the number of neutrons that you have. So for oxygen, that means if you're looking at your atomic number, it's 8. The number of protons is 8. For your electrons, it also has to be 8, right? Why? Because it's neutral. If your atom is neutral, the number of protons equals the number of electrons. But for your number of neutrons, that would be 17 minus 8, which is equal to 9. So that's the number of neutrons that you have because it's based on your atomic mass, which is 17. Again, similarly for potassium, potassium would have 19 for the number of protons because it's its atomic number. And then the number of electrons is also 19 because it's a neutral atom. However, the number of neutrons would be 39 minus 9, which is equal to 20. So that's the number of neutrons of potassium. So for uranium, which is U, the number of protons is 92. However, the number of neutrons is going to be 235 minus 92, right? Because it's atomic mass minus the atomic number, which gives you the number of neutrons. If at any point you can't see my screen, please let me know so I can shift my camera. Okay, so 235 minus 92 would give us 143. So the number of neutrons of uranium is 143. Now if you go and look at the number of electrons, because it's neutral, right? Your atom here is neutral, therefore the number of protons equals the number of electrons, which is 92 as well. Hopefully that was straightforward for your neutral atoms. Now we go into cations and anions. So for cations, right, so we know that this is +2, it's a cation. That means the number of protons still remain the same, which is 12, right? Because that's our atomic number, which is 12. And the only change here is the number of electrons, because as you remember, if we were looking at our periodic table, depending on where the element is found in a certain group, right? So say for example, this is group 1. So this is group 1, this is group 2, and then you have 3 until 8, right? So your elements that are found in group 1, group 2, group 3, and group 4, they're most likely going to lose that electron to gain that full octet, because at the end of the day, everyone wants to be stable. That's why they just prefer to lose that valence electron to gain that full 8 electrons. Does that make sense? And then if you're at group 5, 6, and 7, that means you're just likely to gain electrons as opposed to losing it, because it's just easier for you to do it that way, since you already have 5 valence electrons and you have 6 and you have 7, right? Because if you think about, if you have 7 valence electrons, it's just easier for you to gain 1 more electron to achieve that full octet, as opposed to getting rid of the 7 valence electrons, right? Because it would require you more energy in that sense. So that's why for the number of electrons, I tell my students that if you're looking at the number of protons that you have, you would have 12 minus 2, which is 10. So now you have fewer electrons if you're a cation. So the number of neutrons would still remain the same, which is 24, atomic mass minus atomic number, which would give you 12. Okay, hopefully that makes sense. Now moving on to anions, which is S minus 2. So the number of protons is still 16, but the number of electrons, right? Because it's an anion, that means you have a tendency to gain 2 more electrons in this case, because it's minus 2. So you would have 16 plus 2, which is 18. So you have more electrons now. But for your number of neutrons, it's still the same. You would have 32 minus 16, so atomic mass minus atomic number. So that would give you 16 as well. So that's the number of neutrons that you have. Okay, so since we're on this cation and anion topic, I just thought of bringing this up. So as you notice, for the number of, let's say, electrons, right? This is 10 and this is 18. So you've probably learned in class about your periodic table trends, like how do you know which atom is going to be larger and things like that. So we're concerned about atomic size in this case. So if, for example, you're looking at 10, right? So say, for example, this is magnesium plus 2, and you're comparing this with Mg, right? So just the neutral magnesium atom. So magnesium, if you recall, it's found in group 2. So it has atomic number 12, right? That means it has 12 electrons, right? Because it's a neutral atom. So 12 protons equals 12 electrons. So you have 12 electrons for the neutral state of magnesium. So if you're comparing this thing, sorry, let me just delete this. So if you're comparing the neutral magnesium atom versus Mg plus 2, which atom is going to be larger, if that's the question? That means this right here, this is going to be a larger atom, right? The neutral magnesium atom is going to be larger compared to Mg plus 2. And the reason for that is because you have greater number of electrons, which is 12, as opposed to 10 electrons. And if you have more electrons, right, with the same number of protons, which is 12, that creates an electron dispersion. So you're going to have a larger atom because you have more electrons, resulting to a repulsion of the electrons, and that's even greater if you're looking at the neutral state of magnesium. So the more electrons you have, the greater the atomic size. Okay, so just to wrap up, since we have 5 minutes left. Yeah, because for number 12, this would take some time to go over this question. Yeah, so thank you so much for coming in today. I know everyone is concerned about health and safety and social distancing. I hope you guys are also doing that right now. You know, this is not something to put more pressure on you guys. I'm just really concerned, and also OneClass is really concerned, because at the end of the day, we do all hope that things will resume back to normal. So I think it's just really important to stay on top of your studies. And if you want to see more of our live stream, and if you want to put in your requests, please make sure to go to oneclass.com/livestream. And I'd love to hear from you. So thank you so much again for coming in, and I'll see you on my next class. Bye, guys.